Hi, my name is dr. Ahmath. In this video lecture, we are going to discuss about the applications of derivatives. In particular, we are going to discuss about the concavity of the curves and identifying them using the derivatives. So I would like to start this lecture by reviewing the previous topics, previous techniques which we have learned so far. In a previous lecture, we discussed how to identify whether the curve is decreasing or increasing using the first derivative. So if the curve is decreasing, then the tangent line for any point in that region is going to have the negative slope, right? For example, this tangent line has the slope maybe like -1, but if you choose any other point in this region, the tangent line is still going to have the negative slope. And if you remember, the slope of the tangent line is nothing else as the derivative of this curve. And if the slope is negative, it means that the derivative is negative. This is how we are going to understand whether the curve is decreasing. So at the same time, if the curve is increasing, then the slope of the tangent lines are going to be positive. For example, this tangent line is going to have the positive slope, k is equal to 2, for example. Then it is nothing else as the first derivative of this curve, which is positive. It helps us to understand whether the curve is increasing. So we can identify increasing and decreasing regions of the curves by identifying the signs of the first derivative. So when the first derivative is positive, the function is increasing. When the first derivative is negative, the function is decreasing. So when the first derivative is equal to 0, those points are going to be called as critical points. So it is very important for us to remind this technique because we are going to use this in our lecture today as well. So we are going to first of all define so-called concavity or concave upward. So the curve is called concave upward if it is upper than all of the tangent lines. So for example, I can draw the tangent line here or at any other point. So for all of these points, the curve is going to be upper than them. So that is why it's going to be called as the concave upward. So at the same time, analogously, I can define the concavity downward. So the curve is going to be called as a concave downward if it is going to be more downer or below all of the tangent lines. For example, it is below this tangent line at this point, or this tangent line at this point, or even at this below than this tangent line at this point. Okay, so the curve is below than all of the tangent lines. So that is why it is going to be called as the concave downward. What we want is we would like to develop an analytic tool which would tell us whether the curve is concave down or up without actually sketching this. So as we did for the first derivative or for the increasing and decreasing regions, if you remember. So in order to develop this kind of tool, I would like to solve a problem. I would like to do an example by sketching the curve of the function y is equal to the x in the square. If you remember, it's a simple parabola with the following curve, and I would like to find the tangent lines and their slopes at the 3 different points along this curve and try to understand some consequences which I can get from them. So let's try to do this at these 3 points. First of all, I'm going to do this at the point x is equal to the -1. So this is the point x is equal to the -1. Well, can you tell me what is the slope of this tangent line? So by just looking to the graph, you can tell me that this looks like as a -2, right? And you're right, and this is -2 because you can find this by taking the derivative of this curve. It is going to be equal to 2x. And the value of the derivative of this curve at this point, at the point -1, is going to tell you the slope of the tangent line. So the f prime at the point -1, which is equal to the -2, is going to be the slope of this tangent line. I'm going to choose another point along this curve. For example, x is equal to 0. So you can see here that the tangent line is actually a horizontal line. It means that its slope is equal to 0. And you can easily check this from the first derivative of this curve as well. So x is equal to 0. Then f prime of 0 is equal to 0 as well. So it means that the slope is equal to 0. So now I would like to do this for one more point at the x is equal to 1. You can see here this tangent line and the slope of this tangent line, analogously as before, is going to be equal to the value of the derivative of this function at the point 1, which is equal to the 2. Okay, so we found the 3 tangent lines and the slope of those three tangent lines at the 3 different points. And now I would like to put them into one table and try to understand the behavior of the first derivative. Okay, so the first derivative, which is going to tell me the slope of the tangent lines, is going to have the following values: -2, 0, and 2. -2, 0, and 2. So what kind of function this first derivative is? So if I look to this table, I can see that as I'm increasing the values of the x, the values of the f prime of x are increasing as well. So which means that the f prime of x is an increasing function. Right? If you remember, in the very beginning of the lecture, we discussed about the increasing and decreasing functions, and we say that if f of x is increasing, then the f prime of x is positive. So now if I'm saying here that f prime of x is increasing, it means that f2 prime is positive, analogously, right? If f prime of x is increasing, then f2 prime of x, which is the derivative of the f prime of x, is positive. So this is how we are going to identify the concavity or concave upward of the function. So in particular here, if the curve is concave upward, then the tangent lines are going to have the slopes which are going to be increasing as we increase the values of the x. So that is why the second derivative of the curve is going to be positive. So we can easily check this for this example. So the first derivative of this curve is equal to the 2x. And the second derivative of this curve is equal to the 2, which is a positive value for all of the values of the x from -infinity to the infinity. It means that the parabola, the graph of the parabola, is always concave up. So it is very important for us to understand whether the curve is concave up or down. It helps us, for example, to sketch its graph, or it helps us to understand whether it has the local minimum or local maximum. If, for example, the curve is concave up, and it has the critical point, then it is clear that it is going to have the minimum point there, right? Because it is concave up. So we can make the definition now. So let's make the definition. So if the second derivative is positive in some interval, then the curve is concave upward in that interval. Analogously, we can define this for the concave down. If the second derivative is negative in that interval, then the curve is concave down. So, well, it is possible that the second derivative can be equal to the 0. And those points are important points. They're going to be called as inflection points. Where the second derivative is equal to the 0, then those points are going to be called as inflection points. Usually, the curve is going to change its concavity at that point, whether it's from concave up becomes concave down or vice versa. So I can give you this example of this curve from our previous lecture. If you remember, this curve has the equation y is equal to the x cubed plus 1. And if you find the two derivatives of this curve, the first derivative is going to be equal to the 3x in the square. The second derivative of this curve is going to be equal to the 6x. And this is equal to the 0 at the x is equal to the 0, right? And you can see here that this curve is changing its concavity at this point. So before the 0, it's concave down because you can see that it is below than any tangent line, right? It's concave down. And after the 0, it's concave up. It's concave up because it is upper than any tangent line. And at the 0, it is changing its concavity. It is going to be called as an inflection point. Well, I would like to ask you to remember this function y is equal to the x cubed plus 1 and its behavior at the point x is equal to the 0 because it is going to be very much helpful in our next problem. So what I want now is I would like to apply all of the techniques and knowledge which we have learned so far about the first derivative and the second derivative in order to make the analysis on the concavity, maximum minimum points, the critical points, and inflection points for this curve. At the end, I'm going to sketch its curve, its graph, using this analysis. So first of all, I would like to find the derivative of this curve in order to understand increasing and decreasing regions, in order to understand the local minimum and local maximum points. If you take the first derivative of this curve, it is going to be equal to the 4x in the cube minus 9x in the square. Well, I can take x squared, I can take out x squared from the brackets. It's going to be 4x minus 9. It has two zeros, right? At the 2 points, at x is equal to the 0, and at x is equal to the 9/4. Okay, so we call those points when the first derivative is equal to the 0 as the critical points. Okay, so they are going to be the points where the tangent lines are going to be horizontal. Now I would like to put them onto the number line in order to try to understand where the first derivative is positive or negative, which will tell us where the curve is increasing and decreasing. So I'm going to put the 0 here first of all, then I'm going to put the 9/4, then I'm going to draw the signs. So it is going to be positive here. It means that if you choose any value for the x greater than 9/4, for example 3, so the f prime of x is going to be a positive, then it's going to be negative here, then again it's going to be negative here. So we have this minus behavior because of this x in the square. So it means that our curve is decreasing before the 0, it's still decreasing after the 0, and then it starts increasing after 9/4. Okay, so you see so that the curve is decreasing before 9/4 and is increasing after 9/4. It means that this point is going to be called as the local minimum point. Okay, so now we know a lot of information about the curve. We know that it is increasing from 9/4 until infinity. It is decreasing from minus infinity until 9/4. It has a local minimum at this point. So in order to sketch the curve, I think I need more information, and I can use the concavity of this curve in order to understand it better. So let's try to find the second derivative of this curve in order to find the concavity regions. So the second derivative of the curve is going to be equal to the 12x in the square minus 18x. So well, we can take out 6x from the brackets. If you take out 6x from the brackets, what is left is 2x minus 3. Well, it has again two zeros. At the x is equal to the 0, and at the x is equal to the 3/2. And if you remember, the points where the second derivative is equal to the 0 are going to be called the inflection points. Well, we've got two critical points, two inflection points, and now in order to try to understand where exactly the curve is concave up or down, I would like to understand the signs of the second derivative of this curve. So I'm going to put this 2. So I'm going to put this point 0 and this point 3/2 to here. And then I can identify the signs. So it is going to be plus here, minus here, and plus here. It means that the curve is concave up here, then down here, then up here again. So now we know the inflection points, we know the concavity. I think we are ready to sketch this curve. So let's make a summary first of all. So you can see here that this x is equal to the 0 is critical point and inflection point at the same time. And please note that this at the x is equal to the 0, it is not changing its increasing decreasing region, right? So the curve is decreasing before the 0 and it's still decreasing after the 0. Well, I think this x is equal to the 0, it's very much similar point as in our previous example was the x cubed plus 1. If you remember, it was the inflection point where the curve is changing its concavity. At the same time, it's a critical point where the tangent line is horizontal. I think this is the similar point. So at the same time, I can see here that the curve is going to have the local minimum at the 9/4, and also the curve is going to have the concave upward before the 0 and concave downward after the 0, and it's going to be again concave up after 3/2, right? So let me look to this one more time. Okay, so now I think we are ready to do this. I'm going to put first of all this 4 points, or 3 points actually, into the number 9, into the into the graph and try to make the analysis. So these 2 points are the critical points where x is equal to the 0 and x is equal to the 9/4. This point is 9/4. They are the critical points. The derivatives are equal to the 0. It means that the tangent lines are going to be horizontal at those points. And also I've got 2 inflection points. Inflection points are going to be at the x is equal to the 0 and also at the x is equal to the 3/2, right? So at the x is equal to the 0 and x is equal to the 3/2, the curve is going to change its concavity. Well, if you remember, the curve is decreasing before the 0, from minus infinity until 0, and it's concave up. It was plus there, if you remember, plus, minus, plus, right? It's concave up means that it is going to look like this. So if you remember, at the x is equal to the 0, it's an inflection point, and now also it's a critical point. It's changing its concavity. Well, it becomes concave up. If you remember, our parabola, right, also has its inflection point. It becomes like a concave down. It becomes concave up after 0, right? So still, this is concave up after the 0, but it is decreasing, not increasing. So that is why instead of sketching this upper, I'm going to sketch this downer. So I'm going to sketch this like this. Okay, I think it is going to be very much realistic. So the curve is decreasing from minus infinity until 9/4, right? It is decreasing before 0, it's still decreasing after 0. At the 0, it is changing its concavity, right? And also at the point 3/2, it is also changing its concavity from concave down to the concave up. And then it is going to decrease all the way down until 9/4. And if you remember 9/4, it is the local minimum point. It means that it is decreasing before 9/4, and then it starts increasing after 9/4. Then it is going to increase after 9/4, and it's still concave up. Okay, so you see, so for all of the points after 3/2, the curve is concave up. So you see, so it is very useful to know how to make the analysis using the first derivative and the second derivative. We can, for example, sketch the graph of the curves. We can understand the behavior of the curves much, much better. So this was the applications of the derivatives about the identifying the shape of the curves and their behaviors. So thank you very much for your attention. I hope this helpful for you.